Welcome to this next video in the playlist on vector spaces. In this video, what we're going to do is introduce the concept of linear operators. Now, a linear operator is a special type of linear transformation. So if you're not familiar with linear transformations, please watch my video previously in this playlist on linear transformations before watching this video on linear operators. Okay? So, let's now begin with the assumption that we have an understanding of what a linear transformation is, and let's define what a linear operator is. So, a linear operator then is a function which we'll call capital T from a vector space capital V, okay, onto itself. And this is the big difference between a linear operator and a more general linear transformation. In a more general linear transformation, we have a mapping from a vector space, capital V, onto another vector space, but that other vector space doesn't necessarily have to be the same vector space as you started off with. In a linear operator, it's a special type of linear transformation because both the domain vector space and the codomain vector space are going to be the same vector space. Okay, so a linear operator is a map which we'll call T, a function T, so this is the linear operator, this T here, okay, which maps a vector space capital V onto itself. And of course, it can't just be an arbitrary mapping, it does have to obey some special properties which make it a very interesting map between the vector space and itself. And these special properties are the same special properties that we saw that we wanted a linear transformation to obey. So the properties that we're going to insist are true is that for all vectors that you can pick from the domain vector space here, so for all little v and little v bar that you can pick from capital V, we want it to be the case that if you take t of v plus v bar, that is going to be equal to t of v plus t of v bar. Okay, now normally when we state this criterion for a linear transformation, this addition here is addition in the codomain vector space, and this addition here is addition in the domain vector space. Now of course in this case our domain vector space and our codomain vector space are exactly equal to one another, so when t is a linear operator, these two additions are going to be addition in the same vector space, so I might as well colour them in the same colour there. Okay, so remember then back to our video on linear transformations, what this condition effectively says is that if you were to use the linear transformation, this map T, on the addition composition table for the domain vector space here, okay, so if you were to go through and relabel up all of the symbols in the addition composition table according to this map T, then the thing that you'd end up with, the relabeled up addition composition table, all of the compositions in that, all of the additions, the answers to it would be the same as the additions in the codomain vector space. But of course, addition in the codomain vector space, that composition table is exactly the same as addition in the domain vector space in the case of a linear operator, because they're the same. Okay, so effectively it's saying that when we do relabel up the addition law with our linear transformation, all of the actual answers that we would have in that relabeled up addition table would be the same as the answers for those equivalent additions in the initial addition table before it's been relabeled up. Okay, so that is a condition that makes this mapping very, very special, but we're not going to stop there. We're going to insist on a similar thing for scalar multiplication. So this is property number 1 that we're going to insist on. Property number 2 that we're also going to insist on is that you pick any vector from the domain vector space. So for all little v is an element of the domain vector space, and for all elements that you can possibly come up with from the field F, and I will just add in both of these vector spaces, the domain and the codomain vector space, will be over some arbitrary field capital F. So we're working with some vector space V over some arbitrary field capital F here, so I'll just highlight that in. Okay, so pick any little c which is some scalar from the field capital F, which is the field for which these vector spaces are vector spaces over. It must be the case that if we consider t of c scalar multiplied with v, so t of c times v, that this is the same as if you do c times t of v. Okay, so c scalar multiplied with t of v. So we're going to insist that those two things are true. And we know from our video on linear transformations that this condition amounts to saying that if you were to relabel up the scalar composition table in the domain vector space with our mapping T, then all of the compositions in that relabeled up scalar multiplication table, the answers will be the same as the scalar multiplication in the codomain vector space, which in this case is the same scalar multiplication table as we started off with. So in this case, for a linear operator, it means that when you apply the linear operator and use it to relabel up all of the elements of the vector space in the scalar multiplication table, that all of the compositions that you end up with in the relabeled up final product, the answers will be the same as the equivalent scalar multiplication in the original scalar multiplication table. So this mapping doesn't actually destroy any answers. Okay, it doesn't change any answers to what scalar multiplication does. Okay, so those are the two important properties then that we are going to insist that this linear operator obeys. So to summarize then, a linear operator is a function from a vector space to itself which obeys these two incredible properties, which are very, very interesting. These are the properties that make this interesting. We don't just want some arbitrary map from the vector space to the vector space. We want a very interesting map that's going to obey these two criteria. Now, one thing to point out right now is that nowhere in this definition of a linear operator have I insisted that this map here has to be a bijection, and it doesn't need to be a bijection. Okay, so this does not need to be an onto map, neither does it necessarily have to be one-to-one. Okay, it just has to be a map which maps all elements of the vector space onto some other element of the vector space, but it doesn't need to be injective or surjective. So I have not insisted that this is a bijective map. It does not need to be a bijection to be considered a linear operator. Okay, so there is the definition then of a linear operator. What I now want to do is talk about the matrix for a linear operator. And just before I start doing that, let me just stress that these are all linear transformations, so all the theory of linear transformations applies for linear operators, because it's just a special type of linear transformation where we have a linear transformation where the domain and codomain vector spaces are identical, but it still is a linear transformation. So things like the kernel of a linear transformation apply for linear operators as well. The image of a linear transformation, again, that will have a parallel definition for linear operators, because all of these linear operators are, after all, just linear transformations. So anything that is true for linear transformations, you can do it for linear operators. Okay, and one of the things that we're now going to do for linear operators is we're going to consider matrix representations of linear operators. So we've considered in previous videos in this playlist on vector spaces matrix representations for linear transformations. Now we're going to do that all over again for linear operators. And what we're going to see is that it has a simpler form for linear operators because of the fact that the domain and codomain vector spaces are the same. Okay, so let me then tell you what we're going to do. I'll describe to you what we're going to do. So, in order to even do this, we need this vector space, capital V, to be a finite dimensional vector space. Okay, so we can't do this for infinite dimensional vector spaces. So we're going to insist that these are finite dimensional vector spaces, okay? Or indeed, I can just say it's finite dimensional once. It wasn't quite necessary for me to point out that both of these are going to be finite dimensional because, of course, they're the same thing. Okay, but our vector space V over F is going to be a finite dimensional vector space. Now, what I want to do then is come up with a matrix representation for this linear operator. Okay, so what do I mean by this? What I mean is I'm going to firstly devise a basis for my vector space, capital V. That will allow me to associate with all of the vectors in my vector space, capital V, a coordinate vector with respect to that basis. And now what I'm going to do is I'm going to be able to then describe my linear operator here as a matrix which can multiply all of the coordinate vectors of the vectors in here and map them onto the coordinate vectors of vectors in here which is going to be consistent, well, I want it to be consistent with the linear transformation. So I want to find a matrix which will map coordinate vectors in here onto the coordinate vector that they've been mapped onto in here by the linear transformation. Okay, so as soon as I have a basis, I can associate with my vectors in my vector space coordinate vectors, and then I can describe this linear transformation as a map from coordinate vectors in here to coordinate vectors in here, and that is going to turn out to be representable by a matrix multiplying the coordinate vectors. So I'm going to go over this in this special case of a linear operator here. Okay, so what we're going to do then is we're going to firstly need a basis for our vector space capital V, and of course because our vector space is both the domain and codomain of this function, we're going to use the same basis in both of those. Okay, so we're going to have a basis which I'll call capital B, which will be a finite ordered set of vectors. So I'll write them out here, v1, v2, all the way along to vn. Okay, so this is going to be my basis for the vector space capital V, and I'm going to pick one basis and use that throughout this entire exercise. We will come on to the question of what if you decide that you want to change basis, but we'll do that later on. For now, we're just going to use one basis for both the domain vector space and the codomain vector space. And remember, this is a set of vectors with the special properties that it spans the entire vector space and it's linearly independent. And what that overall amounts to, the reason we love bases so much, is it means that any vector in the vector space can be expressed as a linear combination of the basis vectors in one and only one way. Okay, so spanning the vector space means that there is a way, there is a linear combination of the basis vectors that will give you any vector you like in the vector space. Being linearly independent is then amounting to the being only one linear combination of the basis vectors that gives each vector in the vector space. Okay, so if I've got some arbitrary little v is an element of my vector space capital V, then I can write little v as a linear combination of my basis vectors, which I'll do now. C1 times v1 plus c2 times v2 plus all the way on until we get down to cn times vn. Okay, so all of these c's here, c1, c2, all the way down to cn, those are all elements of the field. They're all scalars, so the ci's are all elements of the field. Okay, so I've got my one and only one linear combination of all of the basis vectors, and I'll just highlight up the basis vectors here in red, okay, that will give me this vector little v. Now, we call these scalars that you have to put in front of the basis vectors to give this vector v, we call those the coordinates of the vector v with respect to this basis. And what we can do is collect them all together into a nice column, like so. So we can put c1, c2, all the way down to cn, and this is going to be the coordinate vector of this vector v in my vector space with respect to the basis b. Okay, so this is the coordinate vector with respect to the basis b, and it's a very important concept to understand that if you use different bases, all of your vectors in your vector space would have different vectors, different coordinate vectors representing them. Okay, so we have picked a basis here, we've picked a linearly independent set that spans the entire vector space, and we are now able to associate with all vectors in the vector space a coordinate vector, i.e. a column of elements of the field. Okay, and understand how incredible this is. We are now reducing these abstract objects in this abstract algebraic structure to just a column of elements in the field. We're associating them with these columns of elements in the field. Okay, and this is called the coordinate vector of that vector with respect to the basis b. Okay, so we can now associate with all vectors in my domain and codomain vector spaces then coordinate vectors with respect to this basis b. And the great question that I now want to ask is, if I have a coordinate vector in my domain vector space here, it will be associated with some vector, and that vector will be being mapped onto some vector in my codomain vector space. What I want to know is, if I know the coordinate vector of a vector in the domain vector space, how do I get to the coordinate vector of the vector that will be mapped onto by the linear transformation t in the codomain vector space? So I'd like to find a matrix to represent this linear transformation, and it will take in a coordinate vector of a vector in the domain vector space and spit out the coordinate vector of a vector in the codomain vector space that is mapped onto by the linear transformation T. Okay, so to put this down in a little formula, I'd have something like this. Here is my coordinate vector in the domain vector space, so I'll just try and color code this in some way. So this is my coordinate vector with respect to the basis B in the domain vector space. I'm going to act some matrix on it. So A here is a matrix that's going to multiply this coordinate vector, and it's going to spit out a coordinate vector again with respect to the same basis, but now in the codomain vector space, which I'll call Y. Okay, so my big question now is, how do I get this matrix A? And we can instantly conclude what sort of a matrix it's going to be. It's going to be an n by n matrix, and the reason is that it's going to be multiplying a coordinate vector which has n components here, so it's going to need to have n columns therefore, and it's going to give us a coordinate vector that's also going to have n components, okay, because again we're using the same basis here. This vector space will have the same dimension, so again all vectors in here will be associated with coordinates which have n components, so you'll have n coordinates again. Okay, so the coordinate vector y will also have n components. Okay, right, so how am I actually going to do this? Well, the best way of doing this is to think about what the linear transformation would actually do to some arbitrary vector in the domain vector space. Okay, so let's take some arbitrary little v from our domain vector space, and what we know is that we can decompose this vector little v into its coordinates with respect to our basis b. Okay, so it will be some c1 v1 plus c2 v2 plus all the way up to cn vn, like so. Okay, so now what I've got here is the coordinates of this starting vector with respect to my basis b. So I've got my coordinate vector x here, so this is the good starting point. Now let's think about then what the linear transformation t would do to this arbitrary vector in my domain vector space. Okay, so if we consider what is t of v, then of course it's going to be t of this thing on this side, because this is just equal to this, so I can write it as t of c1 v1 plus c2 v2 plus all the way along to cn vn. Now, because my linear operator t obeys the beautiful properties that I insist a linear operator must obey, then what I can do is break this down. Okay, so firstly what I'm going to do is apply property number 1 here, which says that t of two vectors added together is the same as t of each of the vectors separately, and then add them together afterwards. Now that just says it for two vectors. However, I claim that as soon as it's true for two vectors, it becomes true for an arbitrary finite length of vectors, and let me explain why. Okay, so what I would like to do then is split this up into n separate portions. Okay, and the way I'm going to do this is I'm going to view this thing here, c1 v1, as just being one vector, and then view c2 v2 plus c3 v3 all the way up to plus cn vn. I'm going to view that as a vector. Okay, so if you like, you can view this as your vector v, and this is your vector v bar, and then what you've got is just t of one vector plus another vector. After all, this is just a vector, and this is just a vector, so it's perfectly valid for you to do that. And then of course what you can split this down into is t of c1 v1 plus t of c2 v2 plus all the way along to cn vn. But now you can continue on, because if you consider this mess over here, t of c2 v2 plus c3 v3 plus all the way up to cn vn, you can consider the c2 v2 as a single vector, and then the rest of it, c3 v3 plus c4 v4 plus all the way up to cn vn, you can consider that a single vector. So you can break this down into t of c2 v2 plus t of the rest of it, and hence you can end up continuing this on. This argument goes on and on. You've only got to apply it a finite number of times, so eventually what you'll get is t of c3 v3 plus all the way along to t of cn vn. Okay, so we can indeed split this up in the way that we would logically like to, we can split it into T of C1 V1 plus T of C2 V2 plus T of C3 V3 all the way up to T of Cn Vn. Okay, now what we're going to do is apply property number 2 and pull out this scalar here. So we're going to rewrite this as C1 times T of V1 plus C2 times T of V2 plus all the way up to Cn T of Vn. So I'm just pulling out all of these scalars outside of the linear transformation T. Okay, and there now I've got this nice expression for T of my vector V. Okay, so what I've arrived at then is the fact that actually if you know where the linear operator sends the basis vectors for your domain vector space, then you know everything you need to know about the linear operator. You know where every other vector in the domain vector space is sent, because any other vector in the domain vector space can be written as a linear combination of the basis vectors, and then when you act the linear operator on that linear combination of the basis vectors, it becomes this, just a linear combination of the images of the basis vectors. Okay, so all you actually need to know are what are the images of the basis vectors, what is T of V1, what is T of V2, what is all the way up to T of Vn. And then as soon as you know that, you know where any vector in your vector space is sent. Now let's remember back to what I'm trying to do here. So this is what my vector V is actually going to be sent onto in the codomain vector space. But what am I actually trying to do? I want to know what are the coordinates of this, because remember I want to take a coordinate vector with respect to the basis in the domain vector space and turn it into the coordinate vector in the codomain vector space with respect to the same basis, map it onto that. Okay, I've got the coordinates here, C1, C2, all the way up to Cn, of my starting vector V with respect to the basis B in the domain vector space. I want to try and now get the coordinates of this thing with respect to the basis B in the codomain vector space. So how am I going to do that? Well, what I need to know is more about these things, T of V1, T of V2, all the way up to T of Vn. I need these images of the basis vectors under the linear transformation written in terms of their linear combinations of the basis vectors in the codomain vector space. Okay, so what I need is a linear combination, for instance, for T of V1. I need to know what is this vector, and I want it written as a linear combination of my basis vectors. So let me stress, this is no longer necessarily a basis vector. It could be any old vector in my codomain vector space. So what I now want to do is write this as a linear combination of my basis vectors. I want to know what are its coordinates in my codomain vector space with respect to these basis vectors. Okay, so this is the point where the notation starts to become a little bit more confusing. Okay, I'm suddenly going to throw on you a coefficient with a double index. Okay, so just watch this. It is all going to work out nicely, but initially it does look intimidating. Okay, so what we're going to say is that this is some A11 V1 plus A21, so I'm going to raise the first index here as we go along the different basis vectors, V2 plus all the way up to AN1 Vn. And now what does the second index here of all of these coefficients denote? That's going to denote which basis vector I'm actually looking at the image of. So for instance, if I now look at T of V2 here, okay, this will be A of A12 times V1 plus A22 times V2 plus all the way up to AN2 V2. So this, oh sorry, not V2, Vn here. Okay, so all this A is, all these A's are, Aij more generally, these are just elements of the field. This is just denoting all of these scalar coefficients that I need here. And because I've got so many of them, I've had to create this double index to actually list them off. Okay, so the first index, I'll remind you, the I index, that is going to tell you which basis vector it's actually a scalar coefficient in front of. The second index, j, that is telling you which basis vector we're actually looking at the image of in the codomain vector space, and this will continue on right down to T of Vn here, and this will be the linear combination A1n V1 plus A2n V2 plus all the way along to ANN Vn, and you're actually going to see that these coefficients that we've got here are actually going to form the components of my matrix capital A, but we'll see that in a moment. Okay, so there is a more intimidating but more grown up and less time consuming notation for how we can do this, and it's good to get used to this notation early on, because when you go more advanced in linear algebra and indeed in other branches of mathematics, this notation dominates. You can no longer write things out explicitly like this, and you have to just use the sigma notation. And indeed, if you go advanced enough, they drop the sigma signs and just have, whenever you have a repeated index, it means sum over. Okay, so I'm about to show you some more grown-up notation then here. So more grown up, what we can do is we can write T of Vj. Okay, so I'm now going to generalize, and I'm going to say, okay, let's consider an arbitrary one of these images of a basis vector. So I've got an arbitrary index there, j, which can be between 1 and n. Okay, so this formula that I'm about to write will apply for absolutely all of them, and it's going to be equal to the sum, so it's going to be a sum of scalars multiplied by basis vectors. Okay, so it's going to be the sum from I is equal to 1 to n of, let's work it out, so the second index is going to have to be j, so that it matches with our j here, and the first index is of course going to be I, so we're going to have aij, and then we'll have vi. So what's this saying? You pick a j between 1 and n, fix that in. So if you like to have a concrete example, just imagine j is equal to 1. You'd stick in 1 here for j as well, and then you'd say, okay, now I'm going to sum from I is equal to 1 to n, so I'd have a1, and then I'd have j is equal to 1, so it would be a11 times v1 plus a21 v2, sorry, yes, v2, plus a31 v3 plus all the way up to an1 vn, which is exactly this expression here, and hopefully you can agree that it would also work for all of these other expressions here as well. Okay, so there's my more grown-up way of writing this entire system of expressions here. Okay, so that's why this notation is nicer, because it means that there's less for us to actually write out. It's less work, although of course it does look more intimidating. Okay, now, more grown-up notation then. I'm also going to apply my more grown-up notation, my sigma notation, to this thing here, the linear combination that I have here of the images of the basis vectors. So I'm now going to write T of V here as sigma from j is equal to 1 to n of Cj tvj, and I've specifically used the j here because I used the j here, and I'm about to want to substitute this in place of here. Okay, right, so there is my more grown-up sigma notation for this linear combination of the images of the basis vectors here. So any vector in my domain vector space will be mapped onto something of this form, where these are the coordinates, these CJs are the coordinates of that vector with respect to the basis B in the domain vector space. Okay, so remember what we're trying to do. Why did we even write this out here? We want to write this expression that I've got here in terms of a linear combination of the basis vectors for my codomain vector space, which of course are these basis vectors v1, v2, all the way up to vn. So what I've now done is written each of the images of the basis vectors in my domain vector space as linear combinations, as their coordinates with respect to the bases, the basis vectors in my codomain vector space. So these coefficients here, these are just the coordinates of the images of these basis vectors in the codomain vector space with respect to my basis B. Okay, now what I'm going to do is substitute these in place of the TV1, TV2, all the way up to TVN. Okay, so doing this in terms of my more grown-up notation, what I'm going to get is that T of V which was equal to this sum here. The sum from j is equal to 1 to n of cj, and now what I'm going to substitute in is this expression for t of vj. So the sum from I is equal to 1 to n of aij vi, like so. Okay, so remember what this actually means intuitively. All we've done is stick this purple expression here in for tv1, we've stuck this next expression in for t of v2, and we've stuck this final expression in for t of vn, and obviously we've done all the ones in between as well. So that's all this is denoting. So what would be the next natural step? Again, thinking intuitively in terms of what this means, well, the next natural step would be to expand the brackets, because at the moment we will have c1 times this great big monstrosity, this massive vector, but we know that in a vector space, scalar multiplication distributes over addition, so what we can now apply is distributivity, and indeed what I'm going to do now is bring this inside this bracket here. Okay, I'm going to distribute scalar multiplication over addition, and this will become the sum from j is equal to 1 to n of the sum from I is equal to 1 to n as well, and then we'll have cj aij vi. So all that corresponds to doing is distributing scalar multiplication over addition of the vectors, multiplying out all of the brackets here. Okay, now we'll have lots of things of the form the cj multiplied by this thing here. Next move. What is going to be my next move? Well, my next move is going to be to apply associativity of scalar multiplication with field multiplication, because at the moment I've got the sum from j is equal to 1 to n, the sum from I is equal to 1 to n of all of these things of this form. So you go through all possible i's and j's and add them all together. But let's have a look at these things that we're actually adding together here. We've got some basis vector vi, firstly being scalar multiplied by this element of the field, aij, and then the answer to that scalar multiplication then being scalar multiplied by this element of the field, cj. Now, we know that when we do that, when we have a vector being scalar multiplied by one thing and then the answer being scalar multiplied by another thing, there's an equivalent way of doing it. It's equivalent to firstly multiplying the two scalars together in the field, so taking cj and multiplying it in the field with aij, getting some new element of the field. So this will be an element of the field. I might just mark that on. That will be an element of our field, capital F, and then taking that element of the field and then scalar multiplying that with vi. Okay, so I'm going to replace this here with this here, and all I've applied there is associativity of scalar multiplication with field multiplication. It does not matter basically where the brackets are. Okay, right, what's my next move going to be? Well, remember what we were actually trying to do. We wanted to express this thing in terms of a linear combination of these basis vectors so that we could find the coordinates. Now we're almost done. The problem is at the moment we've got far too many terms because we've got all of these things all added together when j is allowed to vary from 1 to n and I is allowed to vary from 1 to n. Each of the basis vectors will appear in loads of those separate terms is the problem at the moment, because if you, for instance, let I equal 1 here, there's all of the different j's that you can vary over and still have v1 there. Okay, so there's loads of terms that all have v1 in them. Okay, what we want to do is collect all of those terms with v1 in together. Okay, similarly for all the terms with v2 in, and similarly for all the terms with up to vn in. Okay, so I want to now factorize, basically. I want to factor out the vi's. So how am I going to do this? Well, what I'm going to do is swap these sigma signs around, and I'll try and squeeze this in down here. So what I'm now going to have is the sum from I is equal to 1 to n. Okay, and then I'm going to have some monstrosity of a coefficient, and then I'm just going to have vi. So what I now want to know is what is the coefficient that I need to have in front of each of these basis vectors to give me the correct linear combination for TV. Okay, well I want to add all of the different scalar coefficients together that are in front of a vi. Okay, so if with fixed I, imagine I is fixed now, what are all the different scalar coefficients that are going to be in front of vi? Well, that's going to be where we allow j to vary from 1 to n, okay, and I is fixed. So what I need to have here is the sum from j is equal to 1 to n of all of these scalar coefficients. And I might just swap them around, aij, cj, like so. Okay, of course, multiplication in the field is commutative, so I'm perfectly allowed to swap those around like that. And now this addition, there's a subtle thing here. This addition is now not in the vector space, but addition in the field, and I'm allowed to do that because of the fact that scalar multiplication in the vector space, not only does it distribute over addition in the vector space, but it also distributes over addition in the field. So if I was to scalar multiply this great big addition in the field out with vi, I could expand that out and turn it into an addition in the vector space. Okay, so what I've got here is I'm doing a shortcut basically. Rather than scalar multiplying vi for some fixed I by loads of different elements of the field and then adding them together all in the vector space, I'm saying instead let's take all of those scalars that we've got in front of the vi and let's add them all together in the field, get one element of the field and scalar multiply that once by vi, and that's what I've got here now. So these are the coefficients in front of each vi, basically. These are the coordinates then of this vector tv in the codomain vector space with respect to our basis b. So this is what we were seeking. This is the coordinate of my image vector, basically, my answer. Okay, so let's go over the page and interpret this further. Okay, so my coordinates then of my vector y, which remember is the coordinate vector of the answer vector in the codomain vector space. Okay, and I'll denote the coordinates by d, so we'll have d1, d2, all the way down to dn. Writing out an expression then for di, okay, we can bring this expression over here. Di is just the coefficient that will be in front of each vi, so it's going to be exactly this thing here. So I'm going to get that di is equal, now just make sure this is straight, yep, it's going to equal the sum from j is equal to 1 to n of aij, and then it will be cj, like so. So here is my expression for the new coordinates of the answer vector in the codomain vector space in terms of the coordinates of the initial vector in the domain vector space, which is exactly what I wanted to do. Now let's just go back to actually writing this out explicitly. So we're going to sum from j is equal to 1 to n, but now I is not varying, that's some fixed value between 1 and n, depending on which coordinate you're interested in, and it will be ai1 c1 plus ai2 c2 plus all the way along to ain cn. Okay, and this is starting to look very much so like a matrix, because look at this. If I put these coefficients, the aij's, in the matrix like so. So I had a11 here, I had a12 here, all the way along to a1n. Then the next line I'd have a21, a22, all the way along to a2n, and then right down the way until we got to an1, an2, all the way along to ann, like that, and I made a great big matrix like that. My claim is that I could multiply this matrix with my coordinate vector with respect to the basis in the domain vector space, so c1, c2, all the way down to cn here, and then my claim is that this will spit out the coordinate vector of the answer vector for what this vector would be mapped onto by the linear transformation in the codomain vector space. So I'd have d1, d2, all the way down to dn here. Okay, and the reason is, how do we get d1? Well, matrix multiplication, we take this and multiply it by this, add it to this, multiply by this, and on all the way until we had this multiplied by this, and add that on as well. That's exactly what we've got here. That's the exact expression for the arbitrary di. Okay, so if we set I is equal to 1, we'll get the exact expression that I've just explained. This row times this, and then for the second component we'll take this row and multiply it by this, etc., all the way down to the nth row multiplied by this to get the nth component here. So that's the exact expression that we've got written out here. Now, let me just remind you then of where these coefficients actually came from. Where did these a's actually come from? Where did we define what these a's were actually going to be? Well, remember we defined it back here. Okay, they were the coefficients that you had to put in front of the basis vectors to get the coordinates for the images of my basis vectors under the linear operator. Okay, so the aij's, they are the coordinates of the image of the basis vectors under the linear operator with respect to the same basis that we're using to describe both the domain and codomain vector space. Okay, and remember, we varied the first index as we went along the coordinates. So what that corresponds to doing is going down a column. Okay, so to make this utterly explicit, this first column here of entries in this matrix, which we will call the matrix capital A, okay, all of those entries are the coordinates of the image of the first basis vector with respect to the same basis in the codomain vector space. Then going along the second column here, those are the coordinates. That's the coordinate vector of the image of the second basis vector in the codomain vector space written with respect to the same basis, and so on. The nth column here would be the coordinates of the image of the nth basis vector in the codomain vector space with respect to the same basis, capital B. Okay, so that's where the entries then of this great big matrix A actually come from. Okay, so we now have represented our linear transformation with a matrix A here, but note, it is completely and utterly dependent on which choice of a basis you chose for your vector space V. If you used a different basis, this matrix would have to be changed, okay, so that it still represented the same linear transformation. Okay, and sorry, not linear transformation, linear operator. Of course, all linear operators are linear transformations, so I'd be forgiven for saying linear transformation, but I should try and say linear operator. Okay, so in the next video we will dwell on that exact problem, the problem of if I want to change the basis that I'm using to describe my domain and codomain vector space, how do I have to alter this matrix representation of my linear transformation so that it still works and maps the same vectors onto each other. Okay, so we'll do that in the next video.